All right, let's jump in. Today's class recording has started. I'll make a big noise when I move the microphone. So, all right, yesterday we talked about the idea of conservation of energy and, right, summary. No matter what the process, though, the total amount of energy in the universe remains the same. This is what we meant by conservation. Conservation is a concept that applies to many different situations in the universe, not just energy. We'll run into a couple other conservation laws as we go along here, but the idea remains the same, that whatever we have at the beginning is going to be there in the end. It might look a little different, but it's still there, and that's important. All right? So, in this unit, the type of energy that we're really going to concern ourselves with is mechanical energy. Mechanical energy is a summary, or it's a group of energies that's made up of potential and kinetic. So mechanical energy, and a lot of times when I write it, I'll call this ME, so we know, like, that it's mechanical energy, because there's lots of different types of energy. So ME is equal to PE plus KE. One thing to keep in mind, although we won't do very many problems like this, when we talk about this potential energy, we introduced a couple different types of potential energy: gravitational potential energy and elastic potential energy. Most of our problems are going to deal with gravitational potential energy. We might throw in elastic potential energy conceptually, but most of our problems are going to be gravitational potential energy. But keep that in mind, that when we talk about mechanical energy, it isn't just gravitational and kinetic. We also throw elastic potential in there as well. Okay? Good there? But then, yesterday we talked a lot about the idea that in an ideal system with no form of friction, that's the important part, we will see energy being transformed from potential to kinetic and vice versa, but the sum of the two is constant. So if we don't have friction acting on a system, we will see that the sum of potential and kinetic always remains the same. All right? So, that being said, let's take a look here at this picture, which doesn't show up very clearly on the board and doesn't show up very clearly on your sheet. I think it's at the beginning, the top of the second page, I believe. Is that where it is? Okay. So, here's a tragic situation. I like to use this picture because it's a good story that goes along with it, so I used to tell my story all the time. All right, tragic situation, right? Burning building. So there's this lady, and the situation has become so dire that her only option, she feels, is that she needs to jump out of the window. All right? So she goes to the ledge, right? Grabs her essentials, like her purse, because you can't jump out of the building without your purse, right? Okay. And I guess so. And so she takes that step off the edge. At the very moment she leaves the edge, or she steps off of the windowsill, right? Just like when we drop the ball from our hands, instantaneous velocity, 0. And so it says, right, kinetic energy is equal to 0. But she's above the ground, and so she has some height, so she has 10,000 joules of potential energy. But as we saw in our pendulum lab, and as you kind of know, right, as soon as she steps off the ledge, her instantaneous velocity is 0, but she is accelerating because of gravity, right? So she starts to fall. And as she falls, we know what happens to her speed. It increases, but at the expense of the height decreasing. So, as she falls here, right, we can see her potential energy is going down, her kinetic energy is going up, until she reaches the bottom, right? Where if we assume that height to be 0, she has no potential energy anymore, but all of that original 10,000 joules that she started with has been converted into kinetic. All right? Does that make sense? You okay with that? So, two things before we start analyzing this. Okay? This picture always reminds me of two things. One is legit. The other one is just a hypothetical situation. So, here, there's these firefighters down at the bottom holding this big trampoline thing that people are supposed to jump into. And, you know, this is kind of an old picture because nowadays nobody would ever do this, right? If they were really trying to get somebody out of a burning building, they would take the truck that has the big ladder, right, and they'd back it up right to the building, and they'd just be like, hey, step onto this platform, and we'll lower you down, okay? So it makes me think that this trampoline is an obsolete piece of equipment, and that the firefighters perhaps like store it up in the attic of the firehouse. And so every spring when they're doing cleaning, they come across it, and they're like, we need to throw this thing out. And there's one guy who's like, well, what if the truck is broken and we can't even use it? You know, and they're like, all right, I guess we're going to save it then. So they just stuff it back up there for another year. Right. The second thing that this picture reminds me of is the best day of elementary school gym class, parachute day, right? When you walked in that gym and that parachute was on the floor, you're like, yes, this is going to be a good day, right? And you played the popcorn game when you like, you know, you threw the Nerf balls in there and everybody like shook it and the Nerf balls flew out, you know. And so you'd like, everybody like, you know, threw it up in the air and it turned around and you got made like a big mushroom, you know, and but then you were sitting inside of the parachute mushroom, and like, yeah. And then my daughter actually had parachute day like 2 weeks ago. And she told me a new game that was called Sharks and Lifeguards. Mm-hmm. Never heard of Sharks and Lifeguards before. I was like, Sharks and Minnows? She's like, no, Sharks and Lifeguards. Mm-hmm. Yeah, and I was like, yeah, like, and so the way it works is like, you know, people hold the parachute, and there's two sharks that are underneath the parachute, and there people who aren't holding the parachute up have to sit on the ground, and then the sharks are like under the parachute, and they have to run and like grab a kid who's sitting on the ground and pull him in. But there's like kids on the outside, they're the lifeguards, and so if they see a kid being pulled underneath the parachute by the shark, they have to come and save him. And I was like, so is this like a tug of war between kids? And she's like, no, if the lifeguard tags you, then you're safe. That's not how it works. Yeah, I figured in reality that's probably not how it would work, you know. Like maybe with first graders it might be cool, but once they got to like 5th grade, they'd be like, no, we're having a tug of war with a person, so, yeah. But, anyway, so, yeah, parachute day, best day ever, so. All right, sorry, back to some actual life. So, next to the picture of the lady falling out of the building, there is a set of axes, right? There's an X, Y axis. X-axis is labeled time, and even though the Y-axis isn't labeled anything, I'm going to currently label it as energy. Okay? So, Y-axis energy. All right? As we can see from the title of this graph, right? Conservation of mechanical energy in falling objects. If we wanted to put one line on this graph, we could do it right now without any other thinking at all. All right? And I could put, if I wanted to, I could put that line on the graph. Anybody have any guesses about what that line would be? What that line would represent? That line is going to represent mechanical energy. Right? Why? Because what is it telling us about mechanical energy in this lady's fall? Well, what is the title of the graph telling you? Conservation, right? So it's not going to change. Okay? But let's put some other lines on here that represent individual types of energy. Now, before you draw this line, right, let's talk about it, okay? So, first, if we wanted to put a line representing kinetic energy on there, right, what's it going to do? It's going to increase, okay? However, right, we learned, right, that kinetic energy has not a direct relationship, but a quadratic relationship with velocity, yes? So will the increase in kinetic energy be a straight upward sloping line? What do quadratic relationships look like on graphs? Parabolas, or half of parabolas, right? So if we wanted to put a kinetic energy line on this graph, we'd start it here, right? Oh. And at the beginning, it's, all right. At the beginning, it's going to increase a little bit. All right? And then it's going to go up like that. All right? Oh, darn, I was going to do something. Hold on, everybody. Okay? I cut it off a little bit short, and there's a reason why. All right. So, what's the second line we can put on this graph? Potential energy, right? What's potential energy going to do? It's going to decrease, right? But what has to be true about the sum of those two? The sum has to be the same, right? So at the beginning, the kinetic energy is only going up by a little bit. So what's going to happen to the potential energy at the beginning? It's only going to go down by a little bit, right? But then, as we continue on, right, we're going to end up something like this. Okay. Good with that so far? All right. This is the end of this discussion in physical science when you're not in physical science. So now we have to go a little bit farther, right? So, what happens when that person hits the trampoline? They do bounce, right? But let's go back to, we had this discussion a little bit in last September, right? Bouncing involves three things. When you bounce on the trampoline, three things happen. All right? What's the first thing that you start doing right when you hit the surface of the trampoline? You slow down, right? Then what happens at the very, very bottom? You change direction. What's your velocity when we're changing direction? 0. And then what starts happening then? You speed back up and go the other direction, right? So, from a kinetic energy standpoint, sorry, I forgot to label these with colors, right? Red's KE, yellow's PE, G, all right? So, let's do the kinetic energy, okay? Bouncing in relation to the rest of this trip is a real fast situation, yes? Okay. So, when you hit the trampoline, this is going to happen. Boom, boom. Does that make sense? That's your kinetic energy. Okay. But what has to be true about mechanical energy? What's the title say? Conservation. So mechanical energy has to stay the same, right? So if kinetic energy is going down, what has to happen? Potential has to go up, right? Generally speaking, that involves a raise in height, but we don't go anywhere upward when we bounce, right? Okay. What other type of potential energy do we say enters into this discussion? Elastic, right? What happens to the trampoline as you land on it? It stretches out, right? I'm putting the fourth picture on this graph, fourth line on this graph, right? Nope, sorry, wrong one. Does that make sense? Sorry, I should have looked at that. So what's the blue line representing? Elastic potential energy. All right. So, and I say this on recording, hoping that this person will watch it, but so if Ben was here, he would question something at this point. Anybody want to play the role of Ben and throw out a question here? That's not the question I thought Ben would ask, but it's a good question. That's actually the second question after the questions that were asked. Okay? No, it's not. All right. So, we called the end of this girl's fall, this lady's fall, zero potential energy. Meaning, what's the height when she reaches the surface of the trampoline? Zero. But what happens when she bounces? She actually goes under zero. Does that make sense? Not real far under zero, but she does go under zero. Right? So, I'm going to make two changes to this graph actually. Right? One is, I'm going to take my blue height just a little bit under 10,000. Right? No, wait. My bad. A little bit over 10,000. Because what does the yellow line have to do? It has to go below the x-axis just a little bit. Does that make sense? Yes, no, maybe? Alright. Okay. But then, okay, when we bounce, it comes back to the surface, alright? So, John, next question, right? Why does red almost go all the way back up to the top? Well, when she's done bouncing, she's back to what height? Zero, right? That's the height that she was when she did the trampoline, yes? And is the trampoline stretched out anymore? No. So potential gravitational goes back to zero. Potential elastic would go back to zero. So that means what does kinetic energy have to be? All the way back up to the top. Does that make sense? Okay. Well, so that's the next part. What are we assuming in this whole situation? Mechanical energy is conserved. The mechanical energy is conserved only under what condition? No friction. Is this a real graph? Nope, it doesn't happen in real life. Okay? But for the sake of understanding conservation, does it all make sense how the one's changed and the other ones have to change because of it? And at the end of the day, what does the end sum have to be? It's got to be 10,000. That's what it started at. Does that make sense? Okay. But this is not a real life graph. If we actually put some stuff on here, we wouldn't see this. Since we brought that up, right? Let's go to the last page. Okay? Go to the last page of the package. Alright. Here's a picture of a ball that's going up in the air and coming back down. Okay? Picture of the ball going up and coming back down. Notice, right? Nice and symmetrical on both sides, because that's what it looks like, right? Gravity slows it down on the way up, speeds it up on the way back down. Picture on the right-hand side is similar to the picture that we just drew. It's telling you three types of energy: potential, kinetic, and mechanical. Okay? So, let's figure out which one's which. Which one's the kinetic energy graph? Pluses, squares, or solid line? Any guesses? Kinetic energy. Which one's the kinetic energy graph? Pluses, squares, or solid line? Squares is the kinetic energy. How do we know that? What happens to the ball at the very, very top? It stops just for an instant, right? And so these squares are representing the kinetic energy. And that means probably we could guess that the pluses are going to represent what? That's going to be potential. What type of potential? Gravitational, right? Ball goes up in the air, potential energy gets higher. Ball comes back down, it gets lower. And that means, by default, the solid line is going to represent what? Mechanical energy. Is this a real life graph? Yes. Putting a wire in your taking chances. Okay, that's fine. So mechanical energy is decreasing. So is mechanical energy conserved in this picture right here? If it was, the orange line would be horizontal, and it's not. Right? So this is a real life graph. Because when we throw that ball in the air and it comes back down, what is it encountering the whole time that it's flying through the air? Resistance, right? Which, in essence, is friction from air, right? So we see that the mechanical energy is not conserved, all right? However, we talked yesterday in class, even in situations when mechanical energy is not conserved, total energy has to be conserved. And when we were looking at our pendulum graphs yesterday in class, you weren't here yesterday, sorry. I did record a class, so you can watch it if you really want to. When mechanical energy is decreasing, what is that decrease made up from, or made up by? Remember the bar graph on the far right, right? Thermal energy or heat energy. So, if we wanted to add a second or a fourth and fifth line to this graph, it would look a lot like these graphs, which I believe you have at the bottom of your sheet, right? So here's a picture or a graph that shows, and this is a real life graph, that shows the energy of a pendulum as it swings back and forth. The picture on the left, at least my left, I think it's the middle for you guys, right? Yeah. Shows the mechanical energy, and mechanical energy is decreasing. This is a real life graph, right? Mechanical energy decreases as that pendulum swings back and forth, okay? But then I added two new lines to this graph. Dash, dot, right? And then this solid green line. What's the solid green line representing? Total energy, right? That means what is dash, dot, representing? What's happening to dash, dot, in that third graph? It's increasing. As what is decreasing? As mechanical energy is decreasing. So what does dash, dot represent? That's our thermal energy graph, all right? If you took the slopes of dash versus the slope of dash, dot, right? You'd see that they'd be the same, just flipped, right? One be positive, one be negative. Because if one's decreasing, the other has to increase to keep the total energy exactly the same. Good there? We still haven't done any numbers. We'll do numbers on Monday. How's that? Yeah, if you haven't done the quiz yet, make sure we get that taken care of. And have a good weekend. I will see you guys on Monday.